In this video, I will try to run KLEE on some larger projects in comparison to our previous videos. And the 4 projects I have selected are 4 open source projects, so you can recreate the experiments yourselves. So the first open source project that I will try to run KLEE on is a small regular expression compiler. And all of the projects are written in the C programming language. The second project is a simple JSON parser. And the third project is a UTF-8 utility library. And the fourth project is the HTTP parser that is used in the Node.js project. Okay, so we will start with, and also the reason I've selected these projects, there are several reasons I've selected these projects. First, they are not too large, so they are self-contained, which means that they're easy for me to show how to do it in a rather short amount of time. And the source code of these projects are not huge, so we will see results pretty fast in comparison to how long it actually can take. And then also, the smaller they are just in general easier to work with, which makes it convenient for us. The last reason that I've also selected these projects is that the compilation process of them is rather simple, which is pretty important in terms of getting KLEE to quickly run on it. That is not to say that you can't run KLEE on stuff that is complex to compile. It just takes a bit longer time to adapt KLEE into it, because you need to run KLEE on the LLVM bitcode rather than the executable that is produced. Okay, so let's start with the tiny Regex C library. If we just look through the library itself, there's only 500 lines in the core C file. We can see that there are a few functions here, rematch and recompile here, that takes a single char pointer, and we then have a print function. We have some other utility functions here, and we have some more functions here that take a single char and also some char pointers. In order to find out a good function that we potentially can attack, it can often be beneficial to look at the tests. So we will, for example, look at the first unit test you have in here, and we can see what functions in the library does it call. And the important one here is that it calls recompile with the pattern variable, and the pattern variable is simply a char pointer, which means that this function recompile simply takes a char pointer, and that makes it a convenient function to analyze with KLEE, because we already know how we can create a symbolic buffer and pass it to a function, as we have done in the other videos. Okay, so what I will do is I will try to see how difficult, what happens when we throw KLEE at the recompile function here. So we will clone the repository. We will clone the repository here, and we will go into it. And there's no main function in this re.c file, so we can simply append our main function at the end of the library, and then just do our KLEE logic in there and call into the recompile function. And this is very similar to what we have done previously. So on the left side, I will simply open the re.c file. I will add a main function, and we will declare our usual array of 10. Then we will make the buffer symbolic, and we will make all 10 bytes of the buffer symbolic, and we will simply call it R. Then we will also null terminate the buffer, and the reason that we will null terminate the buffer is, in general, when you have in C a function that expects a char pointer and it doesn't have a second parameter that tells you length, it generally expects a null terminated string, which is perfectly fair. So we will do like this, and we will say the last byte of the char is supposed to be a null terminator, and then we will simply call recompile with our r variable. So now we have created a local char array, and we make the 10 bytes of the array symbolic, and then we call KLEE assume to assume that the last byte in the array is a null pointer. So we essentially pass, and then we pass that to the recompile function. So we have essentially now called recompile with a null terminated string, and this whole string, including the null terminator, is 10 bytes in size. So what we're going to do now is the exact same as previously, in that we will compile the re.c file and get the LLVM bitcode as follows, and we will use the -g as well, and so we get debug symbols, which is important if we get, for example, if KLEE finds an error. It's only if we have -d that KLEE will tell us exactly where the error occurred and give us useful information about the actual stack trace and so on. Okay, so we get our usual implicit declaration of various KLEE functions, and we don't care about that in this case, because we know that they will be defined once they are running inside of the KLEE symbolic execution engine. So we will run the, we can also just verify that we actually did get the oh, I forgot to actually emit the LLVM bitcode. I need to, apologies for that. Okay, so now we got the LLVM bitcode, as you can see here. And what we're going to do is we will run KLEE on the compiled bitcode. Let me just clear the screen. And we will use, similar to what we did before, we will use the uslibc version of libc in our KLEE symbolic execution engine. And now we are simply going to run the BC file, and we will see what happens. So it's running now, and it has already found a memory out of bounds. Let's just run it for a little bit more. It has found another memory out of bounds. It tells us the exact lines where the errors happen, and most likely this is some type of overflow of sorts. We can, before KLEE has finished, we can start to look at what are these lines in the source code. We have the source code over here. So let's look at the pattern here. This is line 121, which is where the first error occurred. And so essentially it tells us that this memory read, because that's the only memory read on line 121, can result in it trying to read a place in memory that has not been allocated. Most likely it's because the index variable is increased inside of the while loop. It's increased kind of like uncontrollable in a manner that is not supposed to. So one could imagine that it, for example, if I is increased twice, so we have an I plus 1 here, and if I is increased twice, perhaps maybe it will skip the null terminator and read a byte off in the buffer. I will not go into too much detail with the error code, but we will see the stack trace and error report produced by KLEE in just a moment. Let's just look at what is at line 190, and we can see here there's another case of it trying to read, and let's just it's trying to read a buffer, and most likely it's just again that I here is not really controlled perfectly and may increase a little bit more than it's supposed to. And just to verify that the pattern variable is the buffer that we provide, so it's indeed trying to read memory inside of the buffer that we provide, but it obviously it's trying to read outside of the range of the buffer. Okay, so I will let this one run until it finishes, and if this takes too long I will skip it in the video, but for now we'll just leave it running. Okay, so KLEE just finished, and if we, I think it took about 5-10 minutes. If we look at the hours here, we can see that KLEE was created around 10:36 and our other files was created 10:27, so around 10 minutes. And we can see that KLEE found a lot of different paths, 811,000, and produced a lot of test cases for us. We are essentially only interested in the moment at the error files, and we can see what they are by finding them inside of the KLEE last directory. So here we have the error files, and we can view the various versions of them. So again, the first error occurs at line 121. We already knew that from the output during the KLEE execution. And what we can do, perhaps more interestingly, is seeing what is the input that triggers this memory overflow. And we use our K-test tool for that. And we can see here the actual data that causes it. So right before our null terminator, we have a hat symbol. So if we look at how the code analyzes the hat symbol we have here, then we can see it certainly increases I here with +1, and then it also increases I +1 down here. I wonder if that is what causes the bug. Perhaps it is. I will have to go a little bit deeper into that, although it is I +1 when it accesses the hat. So therefore, it should not really, is I increased more before? I don't think, or afterwards, I don't think it is. I will not go too much into the detail with the root cause analysis. I will have to do that afterwards, and I will then submit the reports to the authors of the program. But nonetheless, we can very quickly see that, okay, in order for us to analyze the root cause of the crash, we have to look at how the parser analyzes the square brackets, the hat symbols, and we can very easily see here is where it analyzes the square bracket, and here is where it analyzes the hat symbol, and then it's probably some of the logic in here that causes it to have an overflow in our when it reads the next char right here. Okay, so let's also look at what is the buffer that triggers the error at line 190, which is here. And I think now I just saw why it caused the overflow in the previous error case, and that's because when we have a square bracket and we have a hat symbol, I +1, I is incremented by 1, and then afterwards it will do a while loop where it increments I again down here. But because we don't have a square bracket right after the buck down, right after the character here, it will actually just keep incrementing I here. Oh, sorry, and most likely that will cause it to again increment I down here, something like that, and then I here will be outside of our buffer. I think that's about right. But let's look at the bug that triggers the error at line 190 here. So we have our bug report here. So we know that it's test number 2096. So we will simply use our K-test tool again, but this time we will do 296.ktest. Okay, so we have it, and the bug is somewhat similar in that we also have the buffer is somewhat similar in that we have a square bracket, and then we have various backslashes, and we have a square bracket here, and then we have some backslashes, and most likely it's because this while loop continues to increment, and it continues to increment, and then there's an off by 1 because it should probably have the null terminator check should be before we start to increase I plus, before we increase I could imagine. But a little bit more analysis is needed in order to verify the actual bugs here. But certainly the small test cases that triggers the bug as well as the line numbers makes it quite easy for us to get into the details with the root cause of the bug. Okay, so let's go to the second example. JSON parser here, and what we're gonna do is we will simply just clone it and navigate into it. And in this case, we only have a single header file, which we're kind of happy with because that makes it easy to compile. And if we just skim through the code, okay, so there's a bit more line here. Now we have 3,000 lines, whereas previously we only had 300 lines in the tiny Regex project. So what I'm gonna do instead is that I'm gonna look at the tests, and we can see, let's look for some simple tests and how they call. There must, we can assume that there must be some type of like, right, we have that right here actually, some type of function that passes a buffer of characters, and that's essentially what we would like to provide, simply a symbolic buffer. So if we could, for example, exchange the payload here variable to be a symbolic buffer, then we can simply call the JSON parse function and see how that goes. So let's do that. What we're gonna do is we will go over to the left side, and the just to clarify, the JSON parse function is inside of the JSON.h file. I would assume it's right here. So that's exactly what, this is the exact function that we will be calling. So what we're gonna do is we're gonna create a, let's call it KLEE test.c file, and we will include JSON.h, and then we will simply have our main function. We will do our usual routine of having a 10 character buffer. We will make it symbolic. And then we will simply call JSON parse r, and we will give it a size of 9 because the length of the string excluding the null terminator is 9. Okay, so that should do the job, and then we're simply going to do our usual routine. Let me just first clean the screen. We will do our usual routine of clang C, and we want the LLVM code, and then we will also get the debugging symbols, and then we will simply compile KLEE.test.c, which we have here. Now we have the BC file here, and we can simply now call KLEE on it. And let's see how that goes. Okay, it seems to be running, and again, I will let this one run for a while. Oh, it actually already found a bug. Okay, line 478. Where is that? Okay, so there's definitely a read here, and it is trying to skip some white space in here. Before I get into the bug, let me actually just let the tool run for itself, and we will see how that goes. And I will pause the video because it will probably take quite a few minutes again, similar to with our tiny Regex, but I will keep watching it so we can see exactly when the how long time it will take for KLEE to finish running this small application. Okay, so the run of the JSON parser just finished, and we can see that it generated, KLEE generated around 850,000 paths and also 850,000 ktest files. We can see that it only found a single memory out of bounds, and let's try and inspect that a little bit more and see what it is. So we have the file here, and we can just check the error report. Probably doesn't tell us a whole lot more, but we can see though from the stack trace we can start to see that okay, it has something to do with it is trying to skip a bunch of skippable characters, and in particular we are in the skip white space function where the error occurs, and 478 as it is here, and we originate from 610, which is here, you see here, and we can start to learn a lot more about the error. Line 1972, 72, which is here, and so it's pretty early in the process of parsing the given string that we provide, but nonetheless, let's look a little bit at how the specific buffer that is triggering the bug, how that looks, and that might tell us a little bit more about the bug itself. Okay, so we can see that if you actually just provide a bunch of new line and tab characters, then we will reach the overflow. Let's just go back to actually the line at 478 here, and we can see that there is certainly a bunch of case statements here for tabs and new lines, and maybe we are in a loop here where offset is just increasing all the time, which is here. So offset is, what is size set to? So we can see offset here is being increased, incremented once in each of these, in this do while loop. And well, the bug actually happens up here. So probably the source buffer that we get here is at some place in the is the buffer here is probably to a pointer somewhere in the buffer where whenever whatever offset is set to here, it is pointing at somewhere outside of the buffer. Okay, so I will have to do a bit more analysis on doing that, but it seems to be fairly certain. There's no size check here on the actual buffer, but I should do a little bit more root cause analysis here. One approach actually might be to run this buffer on the actual executable, for example, with address sanitizer compiled into it, but I won't do that as of now, as we will just stick to the KLEE analysis. And we can certainly see that KLEE gives us a lot of information about where the bug occurs and the stack trace and all this kind of stuff, but it still takes a bit of time to actually analyze the bug to understand exactly why the overflow happens. Okay, so let's do our third example. And also, just to clarify here, the KLEE analysis took about so the KLEE analysis finished 10 minutes past 11, and we started running it around 11:15. So it took about 25 minutes or so. Okay, a little short of 25 minutes. Okay, so let's take our third example, UTF library, UTF-8 utility library. And in this library, we only have a single header file, which is nice because it makes it easy to compile. And if we just scroll through the library, we can see that there are 1,000, 1,200 lines, 1,300 lines. And we have various just normal string functions, but related to UTF-8 strings. And we can essentially just try and analyze each of these. Perhaps we can try and attack the UTF-8 valid function, see if that one is interesting. And let's do that now. So the way I would do that is I will similar to before, just generate a new C file. We will include the UTF-8 library, and we will then simply have our main function and our usual so like template for calling into functions that have a char buffer as parameter. So we will make our buffer symbolic. We simply call it R again, and we will also null terminate it, because naturally this one expects a null terminated string, because it only takes a char pointer, and if it wasn't null terminated, it kind of wouldn't know when the ending of the function, when the ending of the buffer is, which is perfectly valid. Okay, and let's just call UTF-8 valid with our buffer. And let's see how that goes. We will compile it in our usual way. And we now have ignoring the, okay, that's fine. We don't care about the return value. So it complains because I don't handle the void pointer that is returned from UTF-8 valid, but it's fine in our case. And then we have the implicit declarations of several KLEE functions here, which is also fine because they will be defined once we execute the BC file inside of the KLEE symbolic execution engine. So we will simply just launch it and see how that goes. What happened here? Oh. Okay, so it's running now. And well, it completed very fast, and it didn't find any errors in UTF-8 valid, which is very nice. It explored around 3,000 paths, and that was essentially perfect. So we can we could, for example, try and call it into some other interesting functions. Let's try this one because there's a little bit more substance. So if we call UTF-8 in case compare, let's see what happens if we do that. We can just modify our already existing so like KLEE driver in a certain sense, and we will just, because now we need to have 2 pointers we need pointers to 2, although it's void pointers here, we will just treat them as char strings, and then we will have a size of whatever our bytes are. Notice here that this is not necessarily the correct way of calling this. What I'm gonna do now is not necessarily the correct way of actually calling this function. So we might get kind of a false positive because we treat the function in a way that it should not be treated. They might have some implicit kind of contract that says what we provide to this function, to the UTF-8 in case compare, might be, it can only be valid it can only be valid UTF-8 code, which is not really what we are doing here. So we will do like this. We have just declared a new local buffer and then also made that symbolic, and we also null terminate that. We also null terminate so like the second symbolic buffer that we have. Okay, and then we will just call this one, and we will give it respectively R and R1, and then we will give it a size of, let's do a size of 9 here because we have null terminated strings, and I think that should be fine. R1, R1, R1. Okay, so let's see how that goes, and we will just compile it in the exact same way. We have that here, and again we have a warning here because we are ignoring a return value from the function, so we are returning we are ignoring the integer that is being returned from the function, and we don't really care about that right now. So we will just run KLEE on it again and see what happens. And it's running, and I will just leave it running for a while until it finishes, and then I will I will pause the video in the meanwhile, and then I will return again once the KLEE run has finished. Okay, so I let KLEE run for roughly 4 hours, and then I terminated the application by doing a Control-C. And what you can see here is the results from KLEE. You can see first and foremost that it explored around 300,000 paths, and it found just about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different instances of a memory out of bounds access. So that's quite a lot of different memory out of bounds accesses, and I can imagine that these are actually because I used the because I called into the function UTF-8N case compare with kind of an invalid input, because I gave it just a symbolic buffer, whereas I could imagine that this function actually expects to get a pointer to 2 valid UTF-8 strings, and therefore most likely these will be true positives in terms of they are out of bounds memory accesses. But from the programmer's point of view, most likely I did I called into the function with a data type essentially that wasn't the correct type, and that's perfectly fair for the programmer to have to kind of like require for you to call it with the correct data. Nonetheless, let's look at the different errors. So we can see here we have the line numbers, and we can see that there are 987 is reported at least twice here, and there are also other error memory out of bounds very close to that line number, so 992 and 984. And then we have a bunch of errors, memory errors around kind of like 450 up until 494. There are 2 cases of 494 we can see, and 496 here. 468 happens twice as well, and 481 happens twice as well. Okay, so first let me just show you that indeed it ran for about 4 hours or so. Actually 5 hours. We can see here is our KLEE out directory, and that was made 1822, whereas our previous one where we made our files previously around like 1116. Okay, so let's look at the line numbers here and see what we can find. If we go to 987, we can see that there is a function called UTF-8 code point 987, and we can see here there are multiple memory accesses in the S pointer, and just by looking at it here, most likely it's because we assigned the S pointer to be a given string pointer here, and then we access the first, the second, and the third and the fourth element in this buffer, but most likely it expects the buffer to be a void buffer, meaning it's a 4-byte UTF-8 code point, but most likely the value that KLEE found was if we give it a non-UTF-8 buffer, then we will have a memory out of bounds. Okay, so although this is, it's a true positive from a memory out of bounds perspective, I think it's fair to assume that this is actually just because we give it an invalid UTF-8 string. So that's a conclusion there, and the same error, a similar error occurs at line 992 right here, and the reasoning behind it is most likely the same. And we have also a case on 984, which is in here, and that one is a little bit more interesting because it's actually the first character in the buffer that we access wrong, which most likely shouldn't happen. And that's about it for the memory errors in this function. Let's look at the memory errors around 481. If we scroll up, we have a memory access here, and that's we have S1 here, and we have S2 here, and it's one of these memory accesses that goes wrong. We can try and see if we can identify one of the inputs that that crashes, that causes the out of bounds read or write. And let's go for one of the later ones. Let's see. Let's try and check this one. So if we read the output of that one, we can see that one is in UTF-8 in case compare at 496, which is in fact here. So that's the S2 chart pointer here that we are trying to dereference. That we are trying to dereference 496, and that is most likely out of our bounds, or it is out of our bounds. Let's see what value actually triggers that one. And we want this test file. Let me just, we need this one. Okay, so we have here some hex F0, and we can see that there are at least an F0 here, and there is an F8 here with in our S2 string, and do we have any F8s here? Not really. So I would need to have a little bit more time to analyze these. So yeah, most likely it's F0 here that triggers this if statement to happen, and then for some reason we read further outside the loop, further outside the buffer with the S2 variable, which will be this one, I believe. Okay, so I will not go into much more detail with these memory out of bounds. They do take a bit of time to analyze, but we did find valid buffer overflows, in particular the ones that occurred around 980. They are very real in the sense that it expects a void pointer, whereas we gave it a char pointer, and naturally this is completely fair if you give it a void pointer where every element is 4 bytes long. In our UTF-8 case compare function, that is. So I did some more analysis on the UTF-8 library, and in particular I wanted to write a KLEE driver that was legitimately calling into the UTF-8 library and basically avoid the false positives from the previous KLEE test driver. So I changed the driver a little bit here. We can see we still have the 2 arrays that we could declare here, and we make the bytes symbolic, and we also null terminate it properly. However, then we do 2 calls, one with UTF-8 valid with the R with the first array, and then another call to UTF-8 valid with the second array, and we only call into UTF-8 in case compare in case both of the arrays actually contain valid UTF-8 characters. So this is a legitimate use of UTF-8 as far as I'm aware, and so if this driver finds bug in comparison to the other one, then it's a true bug, else we only call into the UTF-8 in case compare in case we have actual valid UTF-8 code in the buffers. And this argument here specifies the maximum amount of bytes that we want to analyze inside of the UTF-8 in case compare function. So I will try to run this similar to before, and then we will see if KLEE now reports any memory corruption errors. So we compile it in our usual way. And that's perfectly fine. And we can see here we have our new BC file, and we can also see on the dates that I did this experiment just a little bit later than our previous experiments, which we did on August 8. Okay, so now I will run KLEE again by specifying it the usual way, and I will now let it run for a couple of hours, and then we will see what the result is. Okay, so KLEE have run now for the duration of the night, and I will stop it by doing Control-C, and then we can inspect the results that we got. So we can see that we actually found quite a few more memory out of bounds similar to before. I don't think it's quite the same amount. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this time it should be called with valid input in the buffers. So what I'm going to do in this case is, once KLEE just finishes processing, what I'm going to do is try and inspect the results, but instead of inspecting the results as we did previously, where we went through the line numbers and saw where in the source code it happens, what I'm going to do is I'm going to try and replay one of these error cases, but with sanitizer enabled, and then see if address sanitizer picks up the bug as well. Okay, so we can now see that we have roughly 300,000 execution paths. If we look at our errors here, we have our various errors here, and we can take a look at the first one. Okay, this is in UTF-8 code point 987, and if we see what were the buffers that triggered this bug, then we have these buffers. Okay, so what I will now do is I will take this content, I will go into our KLEE-test.c file, I will just post this stuff here. And now I'm going to create two buffers with the values of these strings, of these buffers, and then we will pass that data into our char array 1 and 10. Sorry, to our char array here and our char array here. So I'm going to call this the first one, and then we have the second one, and then we can disregard the content here. Okay, so now we're going to replay this program with the same buffers. We actually have to check here if we will just wrap the UTF-8 end case compare in a if statement, because we need to kind of like force that this is actually being compiled by the compiler that we are going to use now. Okay, so I think this should be good, and we will now compile KLEE-test.c, but this time we will do it such that we have, first we can just compile like this, and then we can try and run it. Okay, everything looks fine. But what if we compile it with address sanitizer enabled? Then address sanitizer will pick up if there is some type of overflow in the execution, and this can also be another way of verifying that the bug exists. Okay, and we did get a heap overflow and a global buffer overflow, which means that it tries to access outside of our R or R1 buffers, and we can see that address sanitizer also catches the bug inside UTF-8 code point, and so on. So here you can see how you can also replay a case, a KLEE kind of like test case inside in a program with address sanitizer enabled, and then see if address sanitizer also verifies the bug. So I will not go into any more details with the result of this UTF-8 code, UTF-8 library, as I will have to do some digging on them themselves. So I reported the bugs in the UTF-8 utility library, and the author of the library kindly told me that I was using the UTF-8 valid function wrong. In fact, it returns 0 on success and the pointer to the offending code point on failure. So that means we need to actually modify our KLEE test a little bit. And we can do it as follows. We will also comment this one out. And we then have to do, if both of them are valid checks, that means if both of them are 0, then we want to do a UTF-8 and case compare on the two arrays. Okay, so I think finally we have a correct implementation, and I should have probably done some more homework, but nonetheless, let's it was very kind of the author to tell me that, and now let's see how this reacts. This here, how KLEE reacts to this analysis. So we will, and that's fine. We have our KLEE function, and we can see now we have the new function here and new binary here, and we will and like this, and now we are analyzing it correctly. So let's wait and see what the result of that is. Okay, so I have run KLEE for the entire day now, and we didn't find any bugs. So it actually occurred. So it actually happened so that the UTF-8 utility library is safe in this UTF-8 in case compare function. And well, so that's a little example of how you can. It's really important to call the function correctly, and otherwise you can naturally enforce memory corruption issues if you don't really treat the program that it's supposed to treat. And there is obviously a concept related to contracts, but I will not go into the details with that. And we can see that KLEE explored roughly 3.5 million different execution paths. So that's a lot of execution paths, and it did so in about 14 hours. So that's it for the UTF-8 example. I would like to move to our fourth example, which is the HTTP parser of the Node.js project. And let's just clone that project first. We are here now, and it's also just this parser is just a simple .c file, so it will be pretty easy for us to sort of like hijack into it, and it will also have some type of HTTP parse function inside of it. But what I'm going to do in this case is I'm actually going to look at the fossers written for this project, and I can kind of do that also because I'm actually the one that contributed the fosser, so I also know this code quite a bit. And if you're interested in fuzzing, you should also check out our website, alogis.com, where we have an online course on fuzzing. But besides that, what I will do is I will take this fosser that I have written here that calls into a function called HTTP parse URL. And this function expects a single char pointer with the size of this of the string that you are passing, and also an integer here, and then also some type of an address to a local struct. And in this case, I will write the function, the kind of like KLEE main function inside of the HTTP underscore parse.c. So we will do our usual routine here, and we will give it array 10. We will make it symbolic, and then we will null terminate the string in our usual KLEE manner, and then we will do what we have done here. There we go, and that should be fine for creating analyzing the HTTP parser symbolically, and this should be good. And the size that we have is a size of 9, and this should be fine. Okay, so now we can actually symbolically analyze the HTTP parser of Node.js. So let's try and do that. And we will compile it in our usual way. We want the LLVM code. And we have our warnings for the usual KLEE stuff, and we don't care about that because they will be defined in our inside our KLEE execution environment. So what I'm going to do now is simply launch it as previously, and I think this should work. And it seems to be running. What I'm going to show here now before I post this video, because I'm pretty sure that the run of this parser will take quite a bit of time, and maybe I will try and run it, let it run overnight. But I will just show that this function is indeed kind of an interesting function to go for HTTP parse underscore URL, which we have here. And we can see that there is quite a bit of logic inside of this function, and it does, I believe it calls into further functions. So and which we have something here. So there is a bit of logic that we can analyze, and if we want to fuzz more, or if we want to symbolically analyze more of the HTTP parser, we can also do, for example, the next fuzzer that I also wrote up here. We can sort of like simulate that fuzzer using the we can adapt the logic from that fuzzer to write like a KLEE driver to the target program. Okay, so on the left side here we have KLEE is now running to symbolically analyze the HTTP parser, and I will leave that for overnight, and then we will see the results in the morning if KLEE has found anything or not. So it actually went quite a bit faster than I expected, and it took, I don't know, roughly around 10 minutes. Yeah, so the KLEE out folder was generated 1904, and we generated the parser 1841, so about 20 minutes. So actually let's try and do one of the more complicated runs, and let's, instead of just symbolically analyzing the HTTP parser parse URL function, let's actually symbolically execute the HTTP parser execute function, which should have a little bit more substance in it, and that should be good for us. So we go ahead and write the same logic as I did previously, and here we will do this, and we will have 9, or we can actually do 10 and then R here, and I think this should be fine. And we actually, given that this HTTP parser execute function takes a size, I think it's actually completely fair if we give it if we don't null terminate our string buffer up here. So I think this should be good to analyze the HTTP parser execute function, which has a bit more possible execution paths in it. Let's take a look at it. And we can see here, okay, so that one has quite a bit more substance, and let's see how KLEE reacts to that. Okay, so I think this is good. We have the parser, it should be both, that's fine. And we have parser, settings, array, 10. Okay, so this should be good, and we will do the exact same thing. And that's perfectly fine. Now we only have a complaint about KLEE make symbolic because we no longer have KLEE assume, and we will run it in our usual way with userlibc, and it's up and running. Okay, so this one will probably run through the night, and I will allow it to do so. Okay, and KLEE is finished now, and it actually went much faster than I expected. KLEE found a total of 135 different execution paths, and the test took around 20 minutes to analyze. So we finished the HTTP parser.bc file 1912, and 35 minutes past 7 the KLEE execution had finished. So, and KLEE did not find any errors both in our first try and also in our second try on symbolically analyzing the HTTP parser, which means that the HTTP parser here is probably quite well written and is free of bugs in the scope that we analyzed the parsers in. Okay, so I think that's it for this video.